Not going to be on
No, you're not going to be on the TV.
Video.
I don't have releases for you people,
That's right.
which means that this isn't going to work as a demonstration for the video. How many of you have visited my my channel on YouTube? We have 2. Okay. Do you know that I have a channel on YouTube?
Yes, you told
Okay,
us.
right. And so this, what I do is obviously I photograph this and I put it up. This is not going to work because the camera's pointed this way and you're over there. So clearly this demonstration is going to be a failure as far as the video is concerned. Unless, of course, all of you want to send releases, which I'm not about to do. I don't have releases. So what is this that I've just handed you?
Good question.
It's a good question. Notice that this is demarked with black spots along the way,
Yes.
all the way, right? And there are 16 of those
Black
demarcations. 16 of those demarcations, corresponding to this diagram. Okay, this diagram is in fact the universe, and you have the universe in your hands. Okay,
We have the
how could that
universe in our
possibly be?
hands?
The reason is,
Metaphorically.
no, well, not metaphorically. The thing is that it's yes, a metaphor, or is it a simile? The fact is,
No.
the thing is that this is logarithmic and that is logarithmic. Is that a simile or a metaphor?
I don't know.
I don't know either.
Go on with your lecture.
Okay,
I'm sorry.
right. So-
It's neither.
What?
It's neither.
But this is like that.
Okay.
That's a simile.
That's a simile.
Okay, this is
Okay.
similar, you're right.
Okay,
But
okay, that's
it's
similar.
onward and
Like.
upward.
It's
The
a
word like.
simile.
Like is a
Oh,
It
it
simile.
has
has
no
like.
like.
It has no
It's a
like.
metaphor.
It's a metaphor. Okay. So what is true about this diagram is this. First of all, this is the universe, and it is all of the universe, all of the observable universe, and we start out at the sun, and there's the Earth over there. Somewhere there's the moon. See the difference between the Earth and the moon? Okay, that is one of these lengths. One of these lengths. Okay, from the Earth to the moon is one of these lengths.
Just like this.
Right. What?
This one?
No. From here, from this to this point, from this black mark to this black mark, is from the Earth to the moon. The thing is that there are 16 of these lengths, and when you add up all 16 of these lengths, you get the end of the observable universe. How could that be? Because all of you, all very smart people, all of you have been to college and then some, know about logarithms. Okay? So, aha!
Do we fall off the edge of the universe?
If you're not careful.
Okay.
Yes.
Be careful.
Right. So logarithmically speaking, you can get from here to the edge of the observable universe in 16 steps. 16
Big, long steps.
16 steps. Okay, now over here, supposedly I've got a board and I can write 10 to the 1, 10 to the 0, 10 to the 0 is, anybody know? That's 1. Okay?
Everything.
No, 10 to the 0 is 1. We're talking math here, okay? 10 to the 1 is 10. 10 to the 2
Is 100.
is 100.
100.
Good, okay. Let's say that these are, let's say that 1 equals 250,000 miles. That's the distance to the moon. Okay, so that's 1. 10 times 100, 10 times that is 100, is 10 times the distance to the moon, and so on and so on and so on. At some point, when you multiply this number by 10 to the 16, you get the distance to the edge of the observable universe. 10, the distance of the moon times 10 to the 16 gets you to the edge of the observable universe for about 45 billion light years. 45 billion light years gets you to the edge of the universe, which makes this interesting, okay? Because look at this picture. You have seen, we have spent in this class, countless amount of time spending all our time here. And we've spent all our time here because we've basically been here. We've been to pretty much everywhere in this part of the universe. So we just have to go a little bit further and we get to the edge, and we get to the end of the universe. And really, literally, we've been, so if this is a distance from the Earth to the Moon, okay, then you get to Mars, you get to Jupiter, you get to Pluto, you get beyond Pluto, but with just a few of these. I'm not doing the math, so nobody's going to accuse me of getting this right or wrong. But pretty much this much is, we've visited this much of the universe, maybe only this much. Okay, I'm not exactly sure. I didn't prepare this well enough. The point is that the rest of this we've never been to, we unlikely to ever get to.
Not soon.
And this is probably why I spent almost all my time here and almost none of my time anyplace else. If you've been paying attention in class, and then you realize that I managed to not discuss any of this stuff from here to here yet, okay? And we're already at the edge. In other words, I have skipped the universe in order to get to the Big Bang, which is, out at the edge here, and to get to what has been talking about for the last few weeks, maybe even months for that matter. I've been talking about this thing called the Hubble controversy, which is a small thing that you brought up, Elaine, in which it made the newspapers for a couple of weeks, and there was some big conversation about what's wrong with the universe, because different groups of scientists got different answers for the universe, and it started to become important rather than a possibility of a mistake. There's a thing called sigma in the world. Sigma. Okay. If something is off the average, okay, and it's a little bit off the average, like for instance my IQ, okay, is not an average IQ. And I'm sure that all of you in this room have at least, your IQ is at least one sigma off of the average, which means I think, and I forget what sigma is for IQ, I'm just going to take a guess. Let's say sigma is 20 points. So if average is 100, 120 would be one sigma off of normal IQ, okay? Most of you are within the 2 sigma, I would assume, right? So you are 2 sigma off normal IQ. But if you were 3 sigma off of the IQ, you would be really weird, okay? You'd be Stephen Hawkins or Einstein or something like that. That's 3 sigma. When things start to get up to 4 sigma, then things are really significantly different from the average and from what you expect. And when the data has been compounded for figuring out how the universe is, it's almost 5 sigma off. Some group says it's this, and some group 5 sigma away, actually probably 4 sigma away, say it's this. And these groups, each of them claim to have the truth, but they can't both have the truth. Now, it's true, they might both be just a little bit, maybe it's just an error. But at the 4 sigma level, it's unlikely to be an error. And at the 5 sigma level, which we hope to get to, it will not be an error. It is most probably truth. There is really a problem between this group and this group. And we've been discussing in this class what one group had to say. And that group were the people from the Big Bang. The Big Bang people, who listen to the universe for a living, have spaceships that go and listen to the universe, have the theory of general relativity at their fingertips, and can model the universe based upon the cosmic microwave background radiation. And that's all the way out here, at the very, very edge of this picture. At the very edge of this picture, they have modeled the universe, and they have found that the universe has a number associated with it, and that number associated with the universe is 67 somethings or others. And the other group, also experts on the universe, have the number 72. Okay, 67 one group, 72 another group, and the problem is that in the past that wasn't a problem, because this was plus or minus 5, this was plus or minus 5, and there was no problem. Somebody said, well, it's somewhere between these two numbers. But the problem is that those numbers are no longer plus or minus 5. They're more like plus or minus 1. That's 1 sigma. Okay, 1 sigma away is 1. Okay, so that's 1 sigma away. 67 plus or minus 1 is 1 sigma away. 67 plus or minus 2 would be 2 sigmas away, and so on. So when you extend these sigmas, they don't overlap. One group's numbers does not match the other group's numbers, and it's become serious.
Becomes what?
It's become serious.
What is serious?
It's serious.
Constant.
There are two numbers, and they're both right. That's serious. You can't average them anymore, and you can't make a story in which one is right and the other one's wrong. They're both right. So the universe has two numbers. So what are these numbers anyway? Yeah, because that would be useful.
Yes,
fact to
that
know.
might be useful.
Might be useful to know. So these numbers are called H naught, H sub 0. H sub 0, the H stands for Hubble. Hubble is, he has a telescope named after him. The reason he has a telescope named after him is because he did something rather significant as things go. He discovered the Hubble, he discovered that the universe was expanding, and he measured it. Now, he wasn't the guy who thought the universe should be expanding. In fact, one of the first people to think that the universe, shouldn't be expanding was Einstein. He said, the universe might be expanding. I really have to make sure it doesn't. So he invented something called what's the name of the constant? The gravitational constant, the
General theory.
General theory of relativity constant. I forget. Why can't I get that? My brain. He invented a constant to make sure that the universe didn't expand, because his equations, when you let them go, and somebody would go ahead and solve them, as soon as you solved his equations, what happened is the universe would either be expanding or contracting. He didn't like either of those answers, so he introduced this constant, which lambda 0, which prevented the universe from expanding. But other scientists had already said, let's doing one of those two things, and let's go out and check which one it is. And it turns out the universe was expanding. Hubble discovered it was expanding, and he got to come up with the number that corresponds to how much it's expanding. And the number he came up with was something like 100 plus or minus 50. But that's okay, because he was early, and a lot of people tried. He was just the first to try to come up with the number. Now, what is that number? I still haven't told you what the number is. What's the number? What's the number mean? Yeah.
Okay.
So the number is let's see, what do we write on here? Okay, here. The number is megaparsecs, kilometers per second per megaparsec. So aren't you sorry you asked?
Yes.
Okay. Okay, but let's explain what each of those things are. Okay, kilometers a second isn't too hard. Okay, because obviously it's almost like miles per second, which is fast. Okay, so it's 67 kilometers per second. Okay, that's an
Okay,
understanding.
that's-
But megaparsec, what is a megaparsec? A megaparsec is a big distance. This is not a megaparsec.
Oh, what is that?
This is not a parsec. This isn't even a light year. We have to go out to nearest star to get to 1 megaparsec. That is a megaparsec. This is 2 megaparsecs.
Wait.
This is 3 meg. And the universe gets really big. This, from here to here, is 45 megaparsecs. Okay. Now the word parsec is a word that I've always thought that it was an unnecessary word, because everybody in this room knows what a light year is, and a parsec is just like a light year, except it's 3 times bigger. Yeah, right. Why would you do parsec when 3.26 light years is a parsec? Why would you do that? Why would you confuse the rest of humanity by inventing something called a parsec when everybody knows what a light year is? And the reason is because astronomers don't really care what you think, and they care what they think. And what they think is let me see. I want to come up with a unit of measurement which has to do with something that I can observe easily. What I can observe is this. So the Earth goes around the sun, as we've learned, and so here's the sun, and here's the Earth, and it goes around the sun like that. Okay, and off in the distance there are stars. There are stars off there in the distance. There's a star. Okay, happens to be a parsec away. Okay, what is a parsec? Well, let me draw a line to this star and a right angle like that. Okay. See this angle here? That angle between that's caused by the fact that the Earth goes around the sun, and this star seems to move in the sky back and forth as the Earth goes around the sun. That star moves in the sky against the background stars, and it moves because of parallax. And so that star moves back and forth across the sky, and as it moves back and forth in the sky, it traces out an angle of 1 second of arc. 1 second of arc. A second of arc is the same thing as, you might say, well, degrees. Okay, you have a degree. There's 360 degrees in a circle. If you divide a degree, 1 degree, into pieces, the thing that you divide it in is called minutes.
Called what?
Minutes.
Minute?
Yeah.
A second, a degree is broken up into minutes. So there are 60 minutes in 1 degree, and then there are 60 seconds in 1 minute, as you well know. So there's really 3,600 pieces to 1 degree. One of those pieces, one of those 3,600 pieces in the 1 degree is a second of arc, and that's what this is, 1 second of arc. And that's, so if you look out far enough, there is a star that moves through the sky just a teeny itty bitty bit as the Earth goes around the sun, and that is called, this distance now, this distance is called 1 parsec. Parsec. That's 1 distance. So it's just, so the fact is, I could have said light years and not done any of this to you. Okay, you didn't need to know parsecs. I could have been talking light years, but the fact is that the Hubble constant is measured in kilometers per second per megaparsec, and so I needed to say the word, because otherwise the word 67 would mean nothing. The word 72 would mean nothing. Okay, what is it? But still, we don't know what that is. Okay, because it's still.
Could it be that light years, light speed was not known when they came up with parsec?
I don't think so. I think I've been looking at this not so carefully for years, and I think that I don't have a good reason why they would go ahead and invent parsec when they were perfectly good with light years, because I think I really don't know.
Light speed is not known that long. Yeah. Astronomy be older.
I think. See, the thing about the speed of light is not only can you measure it, but you can derive it. There is the speed of light is 1 over the square root of this number and this number. And these are numbers that can be measured in the laboratory. You don't have to go anywhere. You can just sit in the laboratory and measure this number, which has to do with magnetism, and this number, which has to do with electricity, and you can measure those two numbers, take the square root of it, divide it into 1, and that's the speed of light. I think that's the way it goes. I don't know exactly at what point the speed of light was not as well known as a parsec. I really don't know. But it's a good question. I just have thought that they were just, it's like, when astronomers went ahead and demoted Pluto from being a planet, they didn't care what you thought. They just said, oh, hang on, it's not a planet anymore. Okay, so what is the Hubble constant?
What is what?
What is the Hubble constant, which is that H0 that I just erased from the board? What is the Hubble constant? So that's where we're going to find out if the Wi-Fi in this room works, because we changed rooms, and I got here late, and I didn't get to set up the computer to have everything more or less on the screen before I began. So we'll see. By the way, you know what I do when I get home is I edit this video, which means that not only am I preparing this class for a day or 2 days, but then I am editing the video for another day, right? So pretty much that's my week. So even though while I'm vamping here, and you guys can get bored as hell whatever happens, the fact is, I can cut this out. So the rest of the universe. By the way, the fact is that the people who have watched these videos is frightfully small. Frightfully small. I am one of the least viewed websites on the web. Okay.
You have to take up tennis.
Right. Is that what that
You're funny.
is? But I hope that will change, because see, the thing is that what's really true about this class is I think in the entire YouTube universe, there isn't an astronomy class in which there's a class. I mean, the fact that there's a class here, that you're not visible to you, but the fact that you talk, the fact that you make remarks, that you said tennis, however irrelevant that is, the fact is that it's fun, and that I will keep that in.
There's a guy who plays tennis, Tsitsipas or whatever his name is, and he has one of these things on YouTube, and he does other things beside tennis. He's a big whatever he does on YouTube.
But does he have a class? Does he have people in the group?
No, he has people watching him at Wimbledon.
Okay, no. See, okay. Yes, people. Anyway, so the fact is that your remarks become the stuff that makes this work. Okay, so as you know, feel free to raise your hands. So this here is the thing that Mr. Hubble did years ago that made him famous. He he was able to figure out, you can't sit here.
I
That's
was
for the
thinking
teacher.
that I would
You
put the
can't,
chair
oh,
here.
okay, that's a good idea. Excellent. Sorry.
What
Okay.
a bird of paradise you are.
Okay.
Gorgeous.
All right. So what? In order to, first of all, he didn't know what he was doing yet. He was just measuring how fast things are moving away from us, from us. At that time period, and I guess it was around 1920 or something like that. And what he did is he looked at things in the sky, and he said, "How fast are you moving away from me?" And that is something that you can do because the universe has been very kind to us humans to arrange a way for us to tell how fast things are moving away from us. If you look at a light source, and that light source is moving away from you, the faster it moves away from you, the more it becomes redder as you go away from you. And in particular, there are chemical elements, sodium, potassium, hydrogen, helium, and each of them have a characteristic spectrum. And that spectrum is known to astronomers. And when that spectrum, whatever it is, gets shifted towards the red, they can say, aha, that thing is moving away from me by a certain amount, and I can measure the speed. So measuring the speed of things as they move away from you is child's play. And now we're going to need one more chair.
Right, mine too.
Right.
Wasn't there a theory from somebody that the universe was actually not expanding but contracting? What
Well,
happened to that?
it's not a matter of whether it's expanding or contracting. We know it's expanding. The question is whether it's slowing down. Okay, so no one's ever thought really that it was really contracting, except Einstein thought it was a possibility, and that's why he invented his gravitational constant. But in fact, the question is it slowing down? And we have determined over time, in recent years, the answer is no. It's not slowing down.
It's not slowing down.
It's
Okay.
speeding up,
Speeding
which is
up.
the
Speeding
nasty
up, you said?
speeding up.
Yeah.
Right. The universe should be slowing down
Expanding.
because there's gravity, and gravity pulls things. And since the universe was created in the Big Bang, you would expect that after the Big Bang, whatever that is, okay, then the universe would start to slow down because there's all this gravity which would pull it back together again. You would expect that. So the fact that it isn't doing that and is doing quite the opposite is quite upsetting to us all. And therefore we have a new word for that, and that word is
Parallax.
no. Want to guess again?
Dark energy.
Dark energy. Correct. Give that
There you
man. Well, of course he knows.
Nickel.
Of course. Howard knows these things, okay? Howard knew these things before he got to the class.
Right.
Right. So I didn't tell him anything he didn't know. But the rest of you, maybe you didn't know? Okay.
Dark energy, right?
Dark energy. So dark energy makes up 75% of everything. So, okay. So dark energy makes up 75% of everything, and that's why the universe is accelerating at an increased rate all the time
Is it
because of dark energy.
75%?
Yeah.
Laird?
I'm-
Energy? Are you talking about dark matter or dark energy?
Dark energy.
Gee, is 75%?
75%. These are round numbers, okay?
Oh,
The actual
round.
number could be more like 70, but I forget these things.
Okay.
Anybody
okay,
know
okay.
the actual number?
Cool.
76.3.
76.3. You made that up.
Yes, I did.
Okay. Okay. So Hubble goes out and he looks at the universe. You know, the universe is close by, and he says, "Aha! This is going this fast, and this is going that fast, and this is going that fast," and that's what this graph is. Okay. So basically, up here we have speed. Okay. Speed. Things are going faster and faster the higher you go on this. But here's another. The x-axis is distance. Distance. How do you know how far something is away from you given that it isn't written on the star, on the galaxy, or anything else.
But you have a formula for it.
No, you don't have a formula for it.
Isn't there a formula? that
Anyway, you
I
got to
can
raise your
generate?
hand.
Sorry.
Okay.
Isn't there a formula?
No, there's no formula for it.
Okay.
What you're doing here, we're talking about data, and there's no formula for data. You measure data. Okay. So the thing is, how do you know how far these things are away? You know how fast they are going. You just don't know how far away they are. So this scale here is not given to you kindly by the forces of the universe. You have to work hard to figure out how far something is away. And we're going to discuss this. It's called the cosmic distance ladder. And
Cosmic what?
The cosmic distance ladder. And there is, in fact, 1,000 careers, maybe 10,000 careers in astronomy in which people have figured out how far things are away. So I'm not going to instantly tell you how that's done, because it's not done easily. It's done with quite a lot of pain. And there is a lot of ways in which it's done. The fact that it's done in very much different ways is really interesting, and we're going to spend quite some time on that. The cosmic distance ladder we will be spending time on. But nevertheless, without telling you how it's done, notice that there is something wrong with this picture. Okay? Notice that there is this circle on this picture.
Oval.
This oval on this picture. Even if I say something wrong, you're not allowed to correct me
Without
unless
raising-
you raise your hand.
This is not a new problem.
Right.
Okay.
Yes.
The problem is, to me, there is such a thing as entropy.
Right.
So when you say that that planets are speeding away faster
Right.
and faster, entropy is the declination and the desuetude of speed until there's nothing. So how do you square the speeding away with the entropic concept?
Okay. Now you need to know that although entropy is a real word, it has no relevance to this conversation, and I'll explain to you why. Okay? Because entropy has to do with the fact that things become more and more disordered over time. Okay? And they become disordered because of a statistical interaction of each thing with each other thing, so that over time things tend to just become more disordered. You leave a small kid in a room with a lot of toys, and at the end of an hour or so, they've managed to distribute every toy in every corner of the room. That's entropy. Okay, there's no chance that the child will ever reassemble all these things into one place unless they are threatened. Okay. And so even then. So the child is an example of entropy. This is not. Okay, this is not. Okay, so just take it on faith here that entropy is an entirely different discussion. This is the expansion of the universe, and entropy isn't related. Although entropy is related to the expansion of the universe in the sense that the universe becomes more and more disordered over time. So that's true. Okay, that is true, but nevertheless irrelevant to this. Okay, because what's going on here, I'm talking about a pattern which in fact we can discern despite all the disorder in the universe. But if you're interested in entropy, it's right here in this oval. Because in this oval is what's going on here is that while the universe is supposedly, the further you go away, the faster something goes. That's what this line says. The further you go away, the faster something goes away. Okay? Did I say that right?
Yes.
The further out you go, the faster it goes away from you. Okay. That's the Hubble law. That's the Hubble law. Except for this thing right here. This is your entropy. This is the thing that I want to ignore. I want to ignore this. This is the Virgo cluster, let's say 20 million light years away from, or maybe 50 million light years, or maybe megaparsecs. No, parsecs. 50. I'm going to say light years. 50 million light years away from us. And the video, if that number is wrong, I'm going to correct it. Okay, but that's, it's a long distance away from us. There's a cluster of 2,000 galaxies, all in the same area. Okay, and they are not paying attention to the Hubble law because they are quite disordered, and they're doing everything they want to do. Entropically speaking, they are disordered, and they have no care whatsoever for the Hubble law because they are disordered and they're doing whatever. So we need to more or less ignore them because these guys haven't got the news that they're supposed to be lined up along this line. Okay? Yes.
According to physics, that's kind of not possible. You can't just decide to ignore a reality of fact that exists in the millions of quantities of units.
Okay. I'm going to show you why I'm going to ignore it. Watch. Because, see, you might say, well, you shouldn't ignore that because it's important. Okay? I'll show you why it's not important. I think this is the cool part. This is okay. This is why I can ignore that piece. Okay? This is another diagram just like the other diagram, exactly like the other diagram, except that the other diagram fits right there in that little red box. Okay? That's why I can ignore it, because the rest of the data does not care about the fact that the Virgo cluster was misbehaving. The rest of the universe is behaving quite nicely. The further you go away, the better it behaves. And the fact that these things don't line up on the straight line has everything to do with the fact that we don't know what we're doing when we try to figure out distance. If we knew the distance thing, we would get it, it would be better. Maybe there is a little bit of entropy going on here, okay, why these things are off to the side. But the fact is that, and maybe that's why they're off to the side. Maybe they're off to the side because we don't know how to measure distance. But it's important to note that we don't care about the fact that there is this back and forth business. The business of the straight line is what we're interested in. Because what that straight line tells you is the further you go, the faster it goes away from you. And that is big news. That's the big news. The fact that things are going this way and that way, and just because they feel like it, because there's an entropy thing going on, is relevant. There is entropy going on here, but it's not relevant to the conversation we're having about the universe expanding. The universe doesn't behave perfectly according to the way we want it. It has its own idea of how to behave, but it's still, the further you go, the faster it goes away from you. And that's a fact, and there's the data for it. You have the question.
I know it describes the perfect data point line, but isn't, and your discussion last week about gravity changed my mind, because I would have said that there's resistance. The farther out you go, the more distance is covered in these points. More distance is covered, relatively speaking. That's a shorter distance, and as it goes farther away, there's a longer distance each time. And there is no resistance encountered?
No, there's no resistance encountered. There's just gravity. Gravity is it.
And,
it's the entire story.
Gravity does not exert any resistant force upon it?
No, gravity is everywhere. We talked about that last week. Gravity is everywhere, but the fact is that the influence of gravity seems to be irrelevant, almost, because, and I think you got here after I mentioned this, the universe is expanding,
Yes.
but it's not slowing down, it's speeding up. So if there's gravity, there's something anti-gravity that has won the battle over gravity. So there's anti-gravity, and we call that dark energy. So dark energy, so there's gravity, yeah, but there's dark energy, and that's the big deal. And this has nothing to do with any of that, because we're not talking about dark energy here. We're just talking about the expansion of the universe as measured by the redshift, the movement, the change in the speed of the object as you go further and further out, and the distance. Further out you go, the more it faster it moves. That's a big deal. Yes.
I'm just trying to
Yes.
refresh my memory from the beginning. The controversy, the two, because I haven't been here for a long time, but the first two numbers is the controversy over distance.
67 versus 72.
It's really a controversy over distance. It's how
It's a-
you
it's a-
measure distance.
No, it's a controversy
Controversy
over
over-
that. No, the Hubble constant is the
Okay.
slope of this line.
Okay.
It is literally the slope of this
Okay,
line.
that's the first number.
The second number I told you,
Okay.
72, is the
Okay.
slope of this line.
Okay, yeah.
Okay? And the first number I told you, which was 67, is
Right.
not have anything to do with this. It has to do with everything I talked about in previous weeks
Okay,
and in
gotcha,
months.
then
Having
fine.
nothing to do with it, having
Fine,
to do with the
I'll watch.
cosmic microwave background radiation
Right.
and how we get
Okay,
that.
okay.
Right,
Got it.
right.
Okay.
So having spent far too much time on the cosmic microwave background radiation,
Mm-hmm.
I intend to spend far too much time on
I love it.
on this, because this is also interesting, yes.
So when you have an explosion, initially everything does accelerate.
Uh, It accelerates at the instant of the explosion, at the instant
How do
of.
you know that the universe is just not still very young in terms of space and that it's still in the expanding explosion phase?
Oh, okay, okay, that's fair question. How do we know it's not in the initial explosion stage? Stage. That's fair.
That's interesting.
4 billion years.
I never thought about that in the sense of because when you talk about the Big Bang, there is the idea that at the initial explosion, everything after that was in fact a constant rate of expansion. So the rate of expansion was the same from nanosecond to millisecond to such and such. Well, actually, that's not true. There's something called inflation. Okay. There was a little thing called inflation. A little thing called inflation, which got somebody a Nobel Prize for coming up with the idea of, well, you know what? The universe is pretty big today, but I don't see how it got that way unless there was something to really give it an extra kick sometime after the Big Bang, which is known as T = 0, when time begins. And then after time begins, a few incredibly small slices thereafter, in terms of 10 to the minus 32 seconds, sometime after the Big Bang, which happened at 0. And by the way, no matter how many times you slice time, it still doesn't get to 0. So there is, of course, the problem of 0. But we're ignoring 0. We're talking about what happens after 0. Sometime, after 10 to the minus 32 seconds, then there looks like if the universe did a constant expansion, it wouldn't get to be big enough to be as big as it is today. So we figured that out, and somebody said, well, I have an idea. What happens if after the Big Bang, there was a thing called inflation, which inflated the universe? And I could give you numbers, which I could give you, but let me say that any number I give, you can think of, it's bigger than that, faster than that, more ridiculous than that. So at some point, the universe had a ridiculous, it's not fair to use the word ridiculous, but on the other hand, numbers don't do it justice either. The universe expanded, inflated. And that's what you were talking about. How do I know that you're asking the question, how do I know inflation is finished? Because inflation lasted for an incredibly small amount of time and made the universe incredibly big very quickly. And then we say, and inflation ended. And you're saying, well, how do we know inflation's over? Okay? And given that that's a question that you've asked, the answer is, we're not sure. Because the universe hasn't stopped inflating. The universe is currently in the business of exploding faster than it was yesterday. So the universe is expanding at an accelerating rate. So the universe is continuing to explode. So while at first I made light of it, the fact is, it looks as if the universe keeps exploding. Question is, does inflation at the beginning of time have anything to do with the inflation that's happening now? Was there a time of quiescence when the universe wasn't doing any of those two things, was just busily, happily expanding without exploding anymore? And because it's definitely exploding now, and it was exploding then, and maybe sometime in between it wasn't. So this is cool stuff. We don't know a lot of stuff. We don't know a lot of stuff. Yes.
This is very similar to the Kabbalistic notion of the instantaneous spark in time. That was basically what you're talking about, the expansion. That was a split second that it all happened.
I don't know what Kabbalistic means.
From Kabbalah. From
Yes.
the whole mystical, okay, you haven't studied it. Okay, but it's a mystical study that
It's Jewish. It's a
yes,
Jewish
that
thing,
Jews
okay.
have studied for hundreds of years. But what I'm really asking is 4.3 billion years is a time period that is supposedly when the universe started.
No,
No?
no, 13.8, but go on.
Okay, well, 4.3 is what I thought.
Yeah,
Okay,
okay.
13.8. If it's
Little bit of
13.8,
difference.
does that time not play some part in the slowing down of the expansionism that we're talking about? Does it not say, okay, we spent quite a few years in the Hamptons and we're, and it's 13 point so and so years, therefore the expansion has not accelerated to the point where we keep saying it is still not finished.
Okay, so that is all fine and good for poetry, not good for science. Okay, it really has nothing to do with science, what you just said. It is interesting in the sense that you could make a case from it from the point of view of things would be nice if that was the case, but it isn't the case. The universe doesn't have feelings and choices, and we're talking about physics. And there is physics that we don't know the answers to. We have this thing called dark energy. We call it dark energy because we don't have a clue what it is.
Right.
The word dark tells us we don't have a clue. The word energy tells us because it's energetic and pushing outwards. But we don't know what it is. And we think, we don't know. We really don't know. And then this thing called dark matter.
Right.
And we don't know what that is.
Dark what?
It's dark matter.
But I'm gonna know soon because that thing I've been getting on my phone. I'm telling you.
Someone here has.
What? What? Oh, you mean
you're
Ethan
getting
Siegel?
lessons. Oh, on the phone. I thought you were
Ethan
making
Siegel.
a joke.
Ethan Siegel,
I thought
who
you were
is
making a joke.
terrific, is not going to tell you what dark matter is
Well,
any more than I'm going to tell you what dark matter is. He doesn't actually have a. He just knows. He knows this stuff better, but he doesn't know stuff that we all don't know. Do you have something that he has said that
yeah,
you'd like to share?
I'm gonna find it.
Okay, good. That's fine.
Can I just
By the way-
Yeah, yeah. While
ask her
she's
what
doing
this
that.
is?
Yeah.
You're getting astronomy
Yeah, I'm
by
paying-
phone?
Yeah, no.
Oh,
There's
sorry.
there's this guy that I subscribe to and she
Uh-huh.
subscribes to,
Uh-huh.
who writes a piece every week or twice a week or 3 times a week, and he has some really good stuff. And it's not designed. It's not really designed for the lay person, but it is. He goes from the lay to the fairly non-lay person. So people like me can be satisfied, and people like Elaine can also be satisfied with the same stuff. I pay money to this guy on a monthly basis, and I think Elaine does a similar thing.
What
You
is
know.
the number? Or
The guy's name is Ethan Siegel, and if you Google his name, you'll find that you can give him money on a monthly basis if you like on Patreon.com. Patreon.com.
Patriarch?
Patreon.
Patreon. Okay, that's better.
Patreon.com.
Okay,
Yes.
Patreon.com. Okay.
This is very hard to wrap your mind around all of this stuff. And
I thought you knew all this stuff. I've talked about it so many times in the past.
that doesn't mean that we know what the hell you're talking about.
Okay, good.
Or we forget after
Yeah,
we talk.
which is more likely. I can tell you the same thing week after week and it works out.
Yes, please do. There are so many things that it's hard to explain. It just seems to me that science, when they can explain, just makes up numbers and says, ignore this, it's that. When you told us a long time ago something about things that we observe now with the stars or anything is actually they're things that happened a long time ago.
Yeah, of course.
Yeah, not yeah.
Yeah, certainly,
A long time ago.
right.
So that everything that we see and speculate about is not based on what's actually happening now.
Okay.
No.
So how can they actually
But for that
say
matter,
right
for
now
that matter,
things are
what you're telling me right now happened a few gazillion seconds ago also, so I'm not sure what I'm current with what you're saying.
right? I don't know how they can be current.
Because there's light travel time, there's sound travel time, but the fact is that although there is this light travel time, okay, and you seem to continuously harp on the idea that maybe the universe isn't the way that it is now because we're looking back in time, and so long time ago it was like this, but how do we know it's like that now is, I think, the ongoing question which you continuously ask, and I'm going to really have to think about that. In the sense of that I can dismiss it easily, but to actually, to give you an honest to goodness answer is not something that I can easily do. I would say we scientists know that it's okay. We know there are things, look, if you look at the picture of the universe from a long time ago, it actually doesn't look the same as it looks now. The universe was different in the past. We know that. For example, we live in a place called the Milky Way. Did the Milky Way always exist? What happened? Was there a time before there was a Milky Way? And the answer is yes, indeedy. The Milky Way was a conglomeration of lots of little galaxies that all came together,
Little galaxies.
To produce the Milky Way. The universe is 13.8 billion years old. The Milky Way might be only about 11 billion years old. Before that, there wasn't a Milky Way. If you look out far enough, the big Milky Ways aren't there. It's only the little ones. You only see the little galaxies. The big ones aren't there. So when I tell you that it's all the same farther out, I do not mean to tell you that it doesn't evolve. I do not mean to tell you that at all. I just mean to tell you the laws of physics don't seem to have changed from 13.8 billion years ago to today. But the galaxies have definitely changed. The universe is different in different places. There are things called quasars. Have you ever heard of quasars?
Yeah.
There are no quasars near us. You know why? Because quasars happened a long time ago in a far, far distant place. And there are none near us because that happened a long time ago. So does that in some way say, I'm not telling you the universe is the same everywhere in time and space. It changes in time. Yes.
But we have only been observing a fraction of a second in time.
No, we've been observing 13.8 billion years worth of time.
How do we know that?
Because
How do we speculate like that?
how do we speculate?
We
Can I-
have looked out
Yeah.
there for such a short period of time.
I will show you a picture. Elaine has something, and then I'm going to show you a picture.
Says
Yes.
new
Get
theory
those old
answers.
pictures because of the time gap, the time delay to some extent, I would imagine.
New theory answers what?
Lingering questions in physics by uniting dark energy and dark matter. The
Yeah.
most primary questions that remain in our understanding of the universe.
And this is written by.
Siegel?
No, this is Robert Lee.
Okay. So the thing is, not to ignore the fact that there. See, you're reading me, and this is your thing. You tend to go with somebody has a theory. Yay! I'm all about that new theory. Think about there's 10,000 astronomers, and that's one of them, and
Well,
he has an idea,
This
and it's not
confirms
necessarily.
another prediction made by Einstein a century ago.
I will read that if you send it to me. But the
Okay.
point is, whether it isn't true yet. This is how things become true in astronomy. In astronomy, somebody says something, okay, and then somebody says, "Well, no, that's not right," and the other people disagree. Okay, what happens is over time, the people who disagree die, and the people who are still living say, well, that's it. So basically, astronomy advances by one death after another until we eventually come to an understanding of the way the universe really is, because the people who disagree die off. Yes.
Is this person who won the Nobel Prize Guth?
Yes.
Okay, so that we're talking about his thing, and I don't know how long he survived on the planet, but his theories have survived for a while.
Right. This guy
Okay.
who came up with inflation, his name is
Okay.
Guth. And frankly, I'm one of these people who don't believe it.
Okay.
But I'm due for
Alright.
death anytime soon. And so the people who actually do believe it will succeed me. And so inflation will become the law of the land, whereas right now I'm still a little bit like, really? Are you serious? This sounds a little bit flaky to me. But there are other people.
The cosmological constant.
Cosmological constant. That's the
That's
Einstein
Einstein
thing.
thing.
Yeah.
Right, I'm gonna send you this now.
Okay.
Okay.
So let me show you. Barbara. Let me show you the universe. Okay. This is known as the Hubble Deep Field.
Hubble Deep
The Hubble Deep Field. The people who run the Hubble Space Telescope agreed to point the Hubble telescope at a spot in space in which
yeah.
nothing was visible at all, and leave it
Just
with its shutter open for a couple of weeks. So they used the Hubble telescope literally to do nothing but take thousands of photographs, which they added together and summed together to get this picture of the universe in that small piece of field. This is the
yeah.
this is you see, that's the moon.
Right.
The Hubble Deep Field is an area of the universe this small.
Oh wow.
Yes.
That's where they were looking for the exoplanets, right? Or like started
No.
in that.
This was
No?
just to look at the universe in a spot in which the universe was dark.
Okay.
It looked one
Okay.
spot in the universe.
Okay.
It would take it to do the work that they did, looking in that one spot in the sky for over 2 weeks. It would take over 1 million years to look at the entire universe at the resolution they looked at this one spot.
Gotcha.
And this one spot looked like this. That one spot looked like this. Look what we see here. There is a galaxy there. There's a galaxy there.
Dear God.
There's a galaxy there. You see all those galaxies? Those are the ones that are close. Those are the ones that are close. See every dot that you see in that picture? Every dot is a galaxy.
Oh dear God.
And the smaller, and we know exactly how far away these things are because of the Hubble law.
The color.
So we can literally say this one is closer, not because it looks bigger, because Hubble law tells us that this one has a smaller redshift. We can see that, so it's closer. These have a bit greater redshift, so they're further. So as we look back in time, we see this is a picture of the universe through time. There's the universe. You can see how it's changed over time. Is this not good enough for you? This is a picture of
you.
the
See that it changed.
because these things, these little ones, are not the same as the ones that are closer. They're smaller. They actually are smaller because they didn't get to build themselves into the major galaxies yet. So they're in the process of combining. What?
How do we know that?
Because they're small. This is a big galaxy. It's been composed of little galaxies that all combine together, but those ones that are far away haven't managed to get together and produce a big galaxy yet. They're on their way to recombining into a larger galaxy. So things change over time in the universe. In this picture, it tells you that. there's 100 PhD theses in this picture telling you all about the evolution of the universe. Because there's only one picture like this because they didn't spend 2 million years looking at the rest of the universe. They couldn't afford it and didn't have the time, but that's a picture of time.
Going back to what you said about people who die are the ones who lose their theory potency. If you manage to live a long time, your theory will prevail. That doesn't make sense.
No, I didn't say
he
that.
was
I didn't say that.
joking.
No, I wasn't joking.
You're not joking?
No, I'm not joking.
Okay.
This is what this is. I didn't come up with this statement.
Okay.
The statement that science progresses one death at a time
Okay.
was something on the Stephen Hawking's, for
Okay.
example, would have said this, not me. Okay, I'm just repeating it badly.
Gotcha.
But the idea is there are so many theories which over time people objected to, and those objections have disappeared. But the people stayed with those theories over time, and then they just simply disappeared as well. And the theory disappeared with them. That's all. So let's just look at this. I have this. I can press the button on this, and we can see. Let's look at this one. You see, that's a spiral galaxy. But you see, look in this picture. Look in this picture. In this picture, which I've just magnified, there are all these other galaxies. That's a galaxy. That's a galaxy. That's a galaxy. Every dot. There are 10,000 galaxies in this picture. That's just a teeny itty bitty bit of the universe. So if we did a picture of the universe, if we did all of the pictures, if we took the Hubble and did it throughout the universe, we would find something like 2 trillion galaxies that we could see in the picture that we could take of the universe.
Oh my gosh.
Okay?
Is that, can I just ask?
Yeah.
Is that the telescope still on Mount Wilson and you want somebody can, where is the telescope?
This is the one that the astronauts have serviced 5 times. This is the one
this
that's
is
floating
Hubble
above the Earth.
space. Okay, got
It's
it.
the Hubble
Yeah,
Space
okay,
Telescope.
You can't go look at this telescope.
Right, okay.
Got it.
Okay. So I think we'll leave it here for the time being,
Oh.
and I guess we will discuss next the cosmic distance ladder. How do we know how far away those objects were in that graph that I had, that line that tells you where speed and distance. How do we know the distance part of that equation? How do we know? And the answer is carefully. A little bit of work by a little bit of work, and everybody's work piles upon everybody else's work until it all hangs together like a ladder. But every rung in the ladder is done by a different person and a different technique to create the ladder. And that's why they call it a ladder. We'll talk about that next time. Listen,